We dream of the stars. We imagine colonies on distant worlds, fleets of starships crossing galaxies, and humanity spreading across the cosmos like seeds in the wind. Science fiction has painted us as cosmic explorers, destined to conquer the universe. But here is the truth that nobody wants to admit. We have barely left home. Right now, in this moment, humanity is trapped. Not by lack of ambition, not by absence of technology, but by the brutal mathematics of reality itself. We look up at the night sky and see endless possibility, but what we are actually seeing is the largest prison ever conceived. Space is not just big, it is incomprehensibly, devastatingly vast, and we are still crawling at the threshold. Think about what we call space travel today. Astronauts float above Earth in the International Space Station, and we celebrate it as living in space. But they are not in space. Not really. They orbit just 400 kilometers above your head. If Earth were the size of a basketball, the space station would be hovering less than half a centimeter from its surface. That is not exploration. That is barely leaving the driveway. Here is what breaks the illusion even further. Orbital flight is not about going up. It is about going sideways. Incredibly, impossibly fast sideways. The space station does not float because it escaped gravity. It falls toward Earth constantly, but it moves so fast horizontally that it keeps missing the planet. It screams around our world at 28,000 kilometers per hour, trapped in an endless plummet. Gravity has not released its grip. It never does. And that grip is merciless. Reaching orbit demands more energy than almost anything humans have ever attempted. We burn millions of kilograms of fuel just to lift a few tons beyond the atmosphere. Rockets must fight against gravity every single second until they reach orbital velocity. One mistake, one miscalculation, and everything falls back down. Even today, after 70 years of spaceflight, only a handful of nations can accomplish this feat reliably. We look at the moon glowing softly in the night sky and think it seems close. It feels reachable. But that gentle light hides a terrible distance. The moon sits 384,000 kilometers away. To understand that number, imagine driving a car at highway speed without ever stopping. It would take 6 months of continuous driving to reach it. 6 months. For something that looks like you could touch it. And here is the devastating truth. We stopped going there. The last human being to walk on the moon left in 1972, more than 50 years ago. An entire generation has been born, grown up, and grown old without any human travelling beyond low Earth orbit. We reached out once, touched the nearest object in space, and then retreated. Not because we lost interest, but because it was too hard, too expensive, and too dangerous. This is where we stand. Humanity, with all our intelligence and innovation, remains bound to a single pale blue dot. We have sent our machines farther, yes, but we ourselves, these fragile bodies of flesh and bone, have never ventured beyond the Earth and Moon system. We are cosmically local. We are newborns who have barely opened our eyes. But why? What invisible walls contain us? What forces conspire to keep us here, looking up at infinity while remaining forever grounded? The answer lies not just in technology or funding. It lies in physics, biology, and the savage architecture of the universe itself, and understanding these limits is the first step toward breaking them. So let us confront the hard limit. Let us draw the boundary line of human exploration and see exactly how far we have pushed into the cosmos. The answer is humbling beyond measure. The farthest any human being has ever travelled from Earth is 384,400 kilometers. That distance represents the journey to the moon during the Apollo missions. 24 astronauts made that voyage between 1968 and 1972. 12 of them walked on its surface, and then we stopped. That line in space marks the absolute frontier of human presence in the universe. Think about what this means. In the entire history of our species, spanning 300,000 years of existence, we have only managed to send 24 people beyond our immediate neighbourhood. The moon is our finish line. It is the edge of our cosmic map, with everything beyond it labelled as territory where humans have never gone and may never go in our lifetimes. Now consider Mars. The red planet captures our imagination more than any other world. We see it glowing in the night sky, we plan missions, we dream of colonies. But here is the unbreakable fact. No human has ever been to Mars. Not even close. Not even remotely close. Mars orbits the Sun at distances ranging from 55 million to 400 million kilometers from Earth, depending on where both planets are in their orbits. At its nearest approach, Mars is still 140 times farther than the Moon, 140 times farther than the farthest humans have ever gone. The numbers become more devastating when you zoom out further. Humans have never visited an asteroid, never flown past Venus, never approached Jupiter or Saturn, those giant worlds that dominate our solar system. We have never crossed the asteroid belt, never seen the ice giants Uranus and Neptune with our own eyes, never ventured into the Kuiper belt, where frozen worlds tumble in darkness. The entire solar system beyond the Moon remains untouched by human presence. We exist in a tiny bubble. The Earth and Moon system is our entire universe of direct experience. Everything else is theory, mathematics, and images sent back by robots. We are trapped in the shallows while an ocean of space stretches infinitely beyond us. Why? What stops us from going farther? The answer is written into our biology. Our bodies are exquisitely adapted for life on Earth, but they become fragile disasters the moment we leave. In microgravity, muscles atrophy rapidly because they no longer need to fight against weight. Bones lose density at alarming rates, leaching calcium into the bloodstream. Astronauts on the International Space Station lose 1 to 2% of their bone mass every month. A journey to Mars could take 9 months one way. By the time astronauts arrived, their skeletons would be dangerously weakened. Then there is radiation. On Earth, we live beneath a protective magnetic shield that deflects charged particles from the Sun and cosmic rays from deep space. In space, that protection vanishes. Radiation slices through spacecraft walls and human tissue, damaging DNA and increasing cancer risk with every passing day. Long-duration missions accumulate radiation exposure that crosses into genuinely dangerous territory. Add to this the psychological toll. Isolation breaks the human mind. Astronauts on the space station can see Earth below them, a constant reminder of home. But on a Mars mission, Earth eventually shrinks to a pale blue dot, then disappears entirely among the stars. Communication delays stretch to 20 minutes one way. If something goes wrong, there is no rescue. You are alone in the most complete sense of the word. Our biology is the anchor. We evolved for one specific environment, and leaving it turns our own bodies against us. This is the deepest limit, the one written into flesh and bone. We are Earthlings in the most literal sense, and space does not want us there. While human bodies remain prisoners to Earth, our machines have become explorers. They venture where flesh cannot survive, travelling distances that would take human lifetimes to cross. And among all the spacecraft humanity has ever built, one stands alone as the ultimate ambassador to the cosmos. Voyager 1. Remember that name. It represents the farthest reach of human creation into the universe. Launched on September 5, 1977, Voyager 1 began as a mission to study Jupiter and Saturn. But it did not stop there. After completing its primary objectives, it kept going, and going, and going. For nearly 50 years now, this small spacecraft has been screaming away from the Sun at 17 kilometers per second. Every single second it moves 17,000 meters farther from home. It never slows down. It never turns back. Today, Voyager 1 is more than 24 billion kilometers from Earth. That number is so large it destroys intuition. If you tried to count to 24 billion, spending 1 second on each number without sleeping or stopping, it would take you 760 years. That is the distance this machine has covered, measured in kilometers. In August 2012, Voyager 1 achieved something no human-made object had ever done before. It crossed the heliopause. the boundary where the solar wind from our sun gives way to the interstellar medium. It left the solar system's protective bubble and entered the space between stars. Voyager 1 now travels through true interstellar space, surrounded by the cold radiation and gas that fills the galaxy itself. But here is what makes this achievement both magnificent and heartbreaking. It is still unimaginably close to home. The nearest star system to our Sun is Alpha Centauri, sitting 4.3 light-years away. At its current speed, Voyager 1 would take more than 70,000 years to travel that distance. 70,000 years. Human civilization is only about 12,000 years old. Voyager will not reach another star until long after our species might be extinct. And even now, Voyager 1 is fading. It runs on a plutonium power source that decays over time, generating less electricity each year. Engineers have been shutting down instruments one by one to conserve energy. By the mid-2030s, Voyager will go silent. It will continue its journey through the galaxy as a ghost, carrying no signal, no communication, no proof of its creators except for the golden record attached to its side. That record is humanity's message to the universe. It contains sounds and images from Earth, greetings in 55 languages, music from different cultures, photographs of human life, even the sound of a mother's heartbeat. If alien intelligence ever finds Voyager drifting through space millions of years from now, they will discover this artifact. They will learn that once on a small blue planet, a species existed that dared to reach beyond itself. Voyager 1 proves something profound and painful. It shows that we can send our technology farther than we ever imagined, but it also reveals the true scale of space. This spacecraft has been traveling at incredible speed for nearly 50 years. It has crossed the boundary of our solar system, and yet it has barely begun its journey to the stars. It moves through a void so vast that human minds cannot properly grasp it. This is not a failure of engineering. This is the reality of cosmic distances. Space is not just big, it is offensively, incomprehensibly enormous. And Voyager 1, our farthest explorer, is still trapped in our cosmic backyard compared to the scale of the galaxy. But why does space feel so impossibly large? What makes these distances so destructive to our sense of what is possible? To understand that, we need to confront the scale problem directly. Our brains evolve to understand distances we can walk, objects we can touch, and time spans we can experience. We are built for human scale. But space operates on a level so far beyond human intuition that our minds simply break when confronted with the real numbers. This is the scale problem, and it is the single greatest obstacle to understanding why space travel feels impossible. Let us start with light. Light is the fastest thing in the universe, moving at exactly 299,792,458 meters per second. Nothing can move faster. This is not a technological limit, it is a fundamental law of physics. Light speed is the universe's ultimate speed limit, written into the fabric of reality itself. Now watch what happens when we measure cosmic distances using light as our ruler. The Moon sits 384,400 kilometers from Earth. Light covers that distance in 1.3 seconds. When you look at the Moon, you are seeing it as it was 1.3 seconds ago. This is our backyard. This is the farthest humans have ever traveled, and light crosses it in the time it takes to blink. Mars is farther. Depending on where Earth and Mars are in their orbits, light takes between 3 and 22 minutes to travel between them. When Mission Control sends a command to a Mars rover, they must wait up to 22 minutes for the signal to arrive, then another 22 minutes for confirmation. A simple conversation with someone on Mars would have a 44-minute delay between question and answer. Imagine trying to hold a discussion where every response takes nearly an hour. Now leave the solar system entirely. The nearest star beyond our Sun is Proxima Centauri, part of the Alpha Centauri system. It sits 4.24 light-years away. That means light from that star takes 4.24 years to reach your eyes. You are not seeing it as it is now. You are seeing it as it was over 4 years ago. And this is the closest star, the nearest one. Voyager 1, our farthest machine, has been travelling for nearly 50 years and will not reach Proxima Centauri for another 70,000 years. Light makes the same journey in 4.24 years. Our fastest spacecraft moves at 0.064% of light speed, not 64%, 0.064%. We are not even close to the cosmic speed limit. The Milky Way galaxy, our home galaxy, stretches 100,000 light years from edge to edge. Light takes 100,000 years to cross it. Our galaxy contains between 200 billion and 400 billion stars, and we cannot reach even the nearest one in a human lifetime. But the scale problem gets worse. The Andromeda Galaxy, our nearest large galactic neighbour, lies 2.5 million light-years away. Light from Andromeda that enters your eye tonight began its journey 2.5 million years ago, long before modern humans existed. We are seeing ancient light from an ancient past. The observable universe extends 46 billion light-years in every direction. That number is meaningless to human comprehension. Our minds cannot hold it. We can write it down, we can calculate with it, but we cannot feel it. The universe is so large that most of it will remain forever beyond our reach, not because of technology, but because space itself expands faster than light can cross it. This is why space feels impossible. Because it is. Not metaphorically impossible, not challenging, but genuinely impossible given our current understanding of physics. Even light, the fastest thing that can exist, struggles to cross cosmic distances in timescales humans can comprehend. We are trapped not just by our biology, but by the architecture of space-time itself. Even if we could build spacecraft that approach light speed, even if we solve the distance problem with revolutionary propulsion systems, there remains one insurmountable barrier: the human body itself. We are the weakest link in every equation about space exploration. Our biology is not just a limitation. It is a death sentence beyond Earth's protective embrace. Start with what happens to your muscles in microgravity. On Earth, your muscles work constantly against gravity just to keep you upright, to move, to exist. In space, that resistance vanishes. Your muscles stop fighting, and within days they begin to atrophy. Astronauts on the International Space Station must exercise 2 hours every single day, just to slow the degradation. Even with intensive workouts, they lose significant muscle mass during 6-month missions. On a multi-year journey to another star system, this loss would become catastrophic. Your bones suffer worse. Bone is living tissue that constantly rebuilds itself in response to stress. Gravity provides that stress. Remove gravity, and your bones stop rebuilding. They leak calcium into your bloodstream at terrifying rates. Astronauts lose 1 to 2% of bone mass per month in space. After a year, their bones resemble those of elderly osteoporosis patients. On a decade-long interstellar journey, astronauts might arrive with skeletons so fragile they would shatter under their own weight when reaching a destination planet. Then comes radiation, the invisible killer. Earth's magnetic field shields us from charged particles streaming from the sun and high-energy cosmic rays from exploded stars across the galaxy. In deep space, that protection disappears entirely. Radiation passes through spacecraft walls as if they were paper, striking cells and breaking DNA strands. Each impact increases cancer risk and damages tissues throughout the body. Long-term exposure causes cataracts, neurological damage, and cardiovascular disease. There is no way to fully shield against cosmic rays without walls meters thick, which would make spacecraft impossibly heavy. Your eyes deteriorate in strange and unexpected ways. The fluid shift caused by microgravity increases pressure behind the eyeballs, flattening them and causing vision problems that can become permanent. Nearly half of astronauts returning from long-duration missions report vision changes. Some never fully recover. Your immune system weakens dramatically. Studies show that T cells become less effective in microgravity, making astronauts more vulnerable to infections. Viruses dormant in the body, like herpes, reactivate more frequently in space. Small infections that would be trivial on Earth could become life-threatening emergencies millions of kilometers from help. And perhaps most dangerous of all, the mind breaks. isolation is psychologically devastating. Humans evolved as social creatures dependent on community and environmental variety. Lock someone in a metal tube for months or years with only a handful of companions, no privacy, constant stress, and the knowledge that any mistake means death and mental health collapses. Depression, anxiety, and interpersonal conflicts become inevitable. On a journey lasting decades, psychological deterioration could destroy the mission before any physical danger does. Every bodily system requires perfect support. Air must be continuously recycled, with carbon dioxide scrubbed and oxygen replenished. Water must be purified and reused endlessly. Food must be stored or grown for the entire journey. Temperature must be regulated precisely. Waste must be processed. A single failure in any of these systems kills everyone aboard within hours or days. The human body is a miracle of evolution, but it is a miracle designed for one specific environment, the surface of Earth. Take us away from that environment, and we become fragile, degrading, vulnerable machines racing toward breakdown. We were never meant to leave home. Our biology screams this truth with every failing system. But we refuse to accept limits, so we build rockets. Rockets are humanity's answer to the impossible. They are controlled explosions, metal tubes filled with fuel that burns at thousands of degrees, generating thrust through pure violence. For over 70 years, rockets have been our only method of reaching space, but they are not a solution. They are a compromise with physics, and physics always wins. Here is the fundamental problem. Rockets must carry all their fuel with them. Unlike a car that drives on roads or a plane that pushes against air, a rocket has nothing to push against in space. It moves by throwing mass backward at high speed. The faster you throw that mass, the faster the rocket accelerates forward. This is Newton's third law made brutally literal. Action and reaction. Throw and be thrown. But fuel has weight. And here is where the tyranny begins. If you want to go faster, you need more fuel. But more fuel adds more mass. More mass means you need even more fuel to accelerate that mass, which adds more mass, which requires more fuel. This vicious cycle is called the rocket equation, and it is one of the cruelest mathematical truths in space exploration. The numbers are devastating. A typical rocket is 90% fuel by weight. The actual payload, the thing you want to send to space, represents only a tiny fraction of the total mass at launch. The Saturn V rocket that sent astronauts to the moon weighed 3,000 tons fully fueled. The command module that actually made the journey weighed only 6 tons. Everything else was fuel and structure that burned away or fell back to Earth. And once that fuel is gone, it is gone forever. You cannot refuel in space. You cannot pull over at a cosmic gas station. Every rocket is a sprinter that burns everything it has in the first minutes, then coasts on momentum for the rest of its journey. If you do not reach the speed you need before the fuel runs out, you are stuck at whatever velocity you achieved. There is no second chance. This is why rockets fight gravity more than they actually travel. During launch, the rocket must generate enough thrust to overcome Earth's gravitational pull, while also accelerating upward and reaching horizontal orbital velocity. Most of the fuel is burned just getting out of the atmosphere. By the time a rocket reaches orbit, it has already consumed the vast majority of its fuel supply. Deep space missions require even more energy to break free of Earth's gravity entirely. Chemical propulsion, the burning of fuel and oxidizer, is fundamentally limited. The fastest exhaust velocity we can achieve with chemical rockets is around 4.5 kilometers per second. That sets an upper limit on how efficiently we can convert fuel into motion. We have been using essentially the same chemical rocket technology since the 1960s because we have already pushed it close to its theoretical maximum. Engineers have found clever tricks to stretch performance. We use gravitational slingshots, flying close to planets to steal some of their orbital energy and gain speed. Voyager used this technique to visit multiple planets without carrying extra fuel, but slingshots only work if there is a planet in the right place at the right time, and the speed boost is limited by the planet's own motion. Staging helps too. Rockets are built in sections that separate and fall away as their fuel is exhausted, shedding dead weight so the remaining stages can accelerate more efficiently. But staging only delays the inevitable. Eventually you run out of fuel and motion stops increasing. Here is the final truth about rockets. They are sprinters, not marathon runners. They explode with power for a few minutes, then coast in silence for months or years. They cannot accelerate continuously. They cannot adjust course freely. Once the burn is complete, you are committed to whatever trajectory you chose. If you miscalculated, if something goes wrong, there is no turning back. But what if we could build something faster? We have pushed chemical rockets to their absolute limit, so engineers began designing machines that redefine what speed means. These are not science fiction concepts. These are real spacecraft flying right now, breaking records and revealing just how far we still have to go. The fastest human-made object ever built is the Parker Solar Probe. Launched in 2018, this spacecraft is designed to study the Sun by diving directly into its outer atmosphere. To accomplish this suicidal mission, it must move faster than anything humanity has ever created. At its closest approach to the Sun, the Parker Solar Probe reaches speeds of 700,000 kilometers per hour. Let that number settle in your mind. 700,000 kilometers per hour. Fast enough to travel from Earth to the Moon in less than 30 minutes. Fast enough to circle the entire Earth in under 4 minutes. This is speed on a scale that shatters human intuition. But here is the devastating truth. Even at 700,000 kilometers per hour, the Parker Solar Probe is only moving at 0.064% of light speed. Not 64%, not 6.4%, 0.064%. It is the fastest thing we have ever built, and it is crawling compared to the cosmic speed limit. If you pointed the Parker Solar Probe at Alpha Centauri and let it fly in a straight line, it would take 6,500 years to arrive. 65 centuries, the entire span of recorded human history, from the first cities to today, would need to pass again before that spacecraft reached the nearest star. And remember, this is our fastest machine. Nothing else even comes close. Voyager 1, despite being slower in raw speed, has travelled a greater total distance than any other spacecraft, simply because it has been moving for nearly 50 years. Time becomes as important as velocity when crossing cosmic distances. Voyager moves at 17 kilometers per second, about 61,000 kilometers per hour. Compared to the Parker Solar Probe, Voyager is a tortoise. But the tortoise has been running for decades, while the hare only recently started. Engineers know chemical rockets have reached their limit, so they have developed alternatives. Ion engines generate thrust by accelerating charged particles using electric fields. The thrust is tiny, barely enough to feel if you held the engine in your hand. But ion engines can fire continuously for months or years, slowly building up speed over time. The Dawn spacecraft used ion propulsion to visit the asteroids Vesta and Ceres, achieving mission objectives impossible with chemical rockets. Solar sails offer another approach. They use enormous reflective sheets to catch photons from the Sun, gaining momentum from light itself. The thrust is even weaker than ion engines, but it requires no fuel at all. As long as light hits the sail, the spacecraft accelerates. Japan's Immerse spacecraft successfully demonstrated solar sail technology in 2010, proving the concept works in practice. Nuclear propulsion could revolutionize deep space travel. Instead of burning chemical fuel, nuclear thermal rockets heat propellant using a nuclear reactor, achieving much higher exhaust velocities. This could cut travel time to Mars from 9 months to as little as 3 months. NASA and other agencies have designed nuclear rocket engines, but none have flown yet due to cost and political concerns about launching radioactive material. All of these technologies represent genuine improvements over chemical rockets. They are more efficient, more versatile, and more capable of sustained acceleration, but none of them approach the speeds necessary for true interstellar travel. Even nuclear propulsion, the most powerful concept we have tested, would still take tens of thousands of years to reach another star. Speed alone is not enough. We need revolutionary breakthroughs. If current technology cannot break the cosmic speed barrier, then we must invent technology that does not yet exist. Engineers and physicists are designing engines that sound like science fiction, but rest on solid theoretical foundations. These concepts represent humanity's best hope of becoming truly interstellar. Some are decades away. Some may never work, but they are the first real answers to the tyranny of distance. Nuclear thermal propulsion is the nearest term breakthrough. We discussed it briefly, but its potential deserves emphasis. By heating hydrogen propellant with a nuclear reactor instead of chemical combustion, these engines achieve exhaust velocities double that of chemical rockets. This means less fuel needed for the same mission, or faster journeys with the same fuel. Mars missions that take 9 months could be cut to 3 or 4. Outer solar system destinations become accessible within years instead of decades. Nuclear thermal engines could fly within the next 20 years, if funding and political will align. But nuclear thermal is still too slow for interstellar journeys. For that, we need fusion propulsion. Fusion is the process that powers the sun, fusing hydrogen atoms into helium and releasing enormous energy. If we could harness controlled fusion in a rocket engine, we could achieve exhaust velocities of thousands of kilometers per second. A fusion-powered spacecraft could accelerate continuously for months, building up to a significant fraction of light speed. Travel times to nearby stars could drop from tens of thousands of years to mere decades or centuries. The problem is that we have not yet achieved sustained fusion power on Earth, let alone in a spacecraft. Fusion requires temperatures of millions of degrees and precise magnetic confinement. Scientists have been working on fusion reactors for 70 years, always promising a breakthrough within the next decade. But progress is real. Recent experiments have achieved net energy gain for the first time. Fusion propulsion remains theoretical, but it is not fantasy. Then there is antimatter, the most energy-dense fuel theoretically possible. When matter and antimatter meet, they annihilate each other completely, converting 100% of their mass into pure energy. Chemical reactions convert less than 1/billionth of fuel mass into usable energy. Nuclear fission converts less than 1%. Fusion converts less than 1%. Antimatter converts everything. A single kilogram of antimatter meeting a kilogram of matter would release energy equivalent to 43 megatons of TNT. An antimatter engine could reach a substantial fraction of light speed. Some designs suggest 20 to 30% of light speed might be achievable. At that velocity, a journey to Alpha Centauri would take only 15 to 20 years. A human lifetime mission becomes possible. The problem is that antimatter does not exist naturally in significant quantities. We can create it in particle accelerators, but only a few atoms at a time. Producing even a single gram would require energy output exceeding the entire world's annual electricity generation. Antimatter propulsion is theoretically perfect, but practically impossible with current technology. Solar sails, however, can be enhanced. Instead of relying on sunlight, we could use powerful lasers to push the sail. This is the core concept behind Breakthrough Starshot, a project proposed by physicist Stephen Hawking and funded by investor Yuri Milner. The idea is to build ground-based laser arrays that focus enormous power onto tiny spacecraft equipped with ultra-thin reflective sails. The laser beam accelerates the spacecraft to 20% of light speed within minutes. At 20% light speed, a probe could reach Alpha Centauri in just 20 years. It could send back images and data about an alien star system within our lifetimes. The spacecraft would be tiny, perhaps only a few grams, carrying miniaturized cameras and transmitters. But it would be the first interstellar mission capable of returning data before the mission planners die of old age. These technologies are our hope. They transform interstellar travel from impossible to merely extraordinarily difficult. But even with these advances, sending humans remains a challenge of entirely different magnitude.